All right, here we go. Welcome to lesson 9.3, Advanced Algebra Notes. We're going to look at, extending concepts from 9.1 and 9.2 here to use trigonometric functions for any angle. So, kind of see a lot we got to get through. Let's jump in. I'm going to try to keep this to a single video here so we can get it all done in one. Just a very brief kind of what's going on here. Where are we at? Lessons 9.1, 9.2. Well, 9.1 for sure focused a ton on, it was all right triangle trig. Okay, so I'm just trying to give us a little bit of like, where are we at? What's going on here? That was everything here. SOHCAHTOA, that type of stuff. We defined these trig functions, cosecant, secant. That's what we did 9.1. 9.2, we looked at some radians, with this alternate unit of measurement, but kind of standardizing standard form of an angle, or standard position at least, I should say. Maybe standard position is better. I think that's the phrase we use. Of angles, and it allowed us to get on an x and a y axis and say, you know what, we can start talking about angles that measure, 750 degrees. Which was kind of cool. It was our first time looking at, or even potentially negative angle measures, right? We talked about, hey, what's, sketch an angle in standard position of negative 120 degrees, stuff like that, right? So that was part of what we did. We did both of those in radians. So what we're seeing here in 9.3 is almost like a bringing together of the two lessons that we like the right triangle trig. It's great, but it's limited in that, if we're going to do a problem that involves right triangle trig, we have to always stand at an acute angle. Hey, opposite over hypotenuse, opposite over adjacent. And we said, well, yeah, that's great, but there exists a lot more than just acute angles. We see here there's negative angle measures, there's very large angle measures. How can we look at applying these concepts of trigonometry to basically any angle? Okay, so that's kind of what's going on with the lesson, just to set up. So let's jump in here. Let's take a look. We pretty much made these notes in class. The picture for sure, and then these definitions. So I'll kind of lay out what's going on here as maybe you pause, add this, and then kind of let's talk about what's actually going on here. So what we have, we're still talking about angles in standard position, right? Theta is still an angle in standard position. So we're talking, if we had to eyeball it, what is this, 120 degree angle? Sure, fine, something like that. And this terminal side of the angle moving around on this, what we think of maybe as a circle, or what is a circle with a radius r, an unknown number, right? We're just kind of measuring from the origin, the actual xy axis from the origin to here would be some distance, the radius of the circle, and then the coordinates of this point, wherever my arm hits, or whether the terminal side, wherever this side hits the angle, has some coordinates, right? We went left x units, up y units. And so hopefully, you're following that. That's just the setup. That's kind of what's going on here. But the kind of the cool part is this large angle that we're talking about right here, this theta, big old angle, obtuse angle, 120 degrees. We can turn that angle if I use the x and y coordinate of that point, and you can obviously see what's going on. And I drop down to the x-axis and say, you know what? We can turn this angle right here into, and it's actually going to be kind of hard, but we can still use some of that SOHCAHTOA stuff if I stand right at that different theta. Now that's an acute angle, but still start talking about side lengths here. How long is this side right here? We went up y units. That's y units long. How far left did I go in this case? I went x units to the left in my radius. So I've got a triangle that has three side lengths we've defined as x, y, and r. We said, let's stand at this little theta right here and go, hey, I want to know the sign of this little theta. I call it theta prime. This theta right here is opposite over hypotenuse, right? That's how sine works. I'm trying to connect, stuff we've done already. Sine, so sine is opposite over hypotenuse, opposite over hypotenuse. And then that's where we end up with this general definition of the sine of an angle is equal to the y coordinate over its radius of a circle where that terminal side hits a circle. So it's probably a little bit out there for some of us as far as what's going on. So this is kind of like bridging the gap from here's a random right triangle just hanging out in space. This side's 20, this side's 10. Tell me all the 6 trig functions of it. To let's standardize this, use what we know about standard position and say, let's talk about angles on this in standard position by always kind of tracing them back to a right triangle. Okay, because if you think about it, and I know I'm kind of getting tight on space here, if I were to just, I got unlimited space, I guess. If I were to just say, all right, draw me an angle. You sketch as many times as you want. Let's go. I'm going to go negative. Who knows? I've lost track already. Some angle right here. Some humongous negative, or I guess really small angle measure, negative angle measure. I've gone around twice, plus some more. That angle, no matter how big it is, I can turn that back into, hey, that's your spot right there. Okay, fine. We could figure out what the XY coordinate of that point is right there. I could drop down to the x-axis and create a right triangle. And if I know this distance from here to here is x, and then we went up y units, this is y units, whatever those are, we could figure out what this r is, if we called it a circle, radius r, and still, for the big blue theta, everything ties back to whatever that angle is right there, which is kind of cool. So basically, we've laid some groundwork here that's going to allow us to work and do some of this trigonometry for basically any angle. Okay, so let's take a look at an example. Example 1, bridging the gap here a little bit. They're giving us the picture, so it's going exactly what we just talked about there, but actually putting some numbers in it. Okay, so it says let negative 12.5 be a point on the terminal side of an angle in standard position. Okay, great, awesome. So we can actually see it looks like we're going by 4s here on the x-axis. So 4. Can't see me tapping the screen there. So 4, we went left, 4, 8, 12, and then we went up 2, 4, 5. So we're going by 2s on the y-axis. So that's the actual like old school coordinates of that point right there. And I say, hey, that angle, that's a big theta. That's an obtuse angle. From here to here is my theta. And so my question would be, or what's being asked of us is to, all right, tell me all 6 trig functions of that big theta right there. So it's essentially asking us, all right, well, what is the sine? I don't know what the angle measure is, but what's the sine of that angle? What's the cosine of that angle? What's the tangent of that angle? And this should sound familiar. We've done this. We did this way back in 9.1. So, and then their partners, cosecant of that same theta, the secant of that theta, and the cotangent of that theta. Okay, so that same setup, it's asking us for all 6. So what's the deal here? I could go back and look and say, oh, that's my definition there. I'm going to take the approach of, what? I'm going to turn this into what we just talked about. I'm going to turn this into that right triangle right here. Okay, we'll put our little person. It's hard for me to zoom in too far, but I got a little. Let's say we're standing. That's our new theta we're kind of talking about. But instead of x's, y's, and r's, I actually know side lengths from the origin, right? From the origin right here, what's this distance? We already counted it out. It's going by 4s, right? So 4, 8, 12, and it tells us the point right there. It's negative 12. And I'm actually going to do this, which seems a little bit weird. That's a negative 12. So for the length of a triangle, yeah, that's kind of weird to say that side length's negative 12. We'll tie this in here in a second. And then because we did move up, we went up 5. It's a positive. It should be a positive 5 units for this side of my triangle. And like we saw in 9.1, we don't have this radius, right? We don't have this distance, but we should all know that if it's a right triangle, I know 2 of the 3 sides. I could use the Pythagorean theorem, 5 squared plus 12 squared. So that's 25 plus 144 is 169, the square root of that. It ends up, and it's kind of a nice example here where this side length is 13. And here's where that negative comes in. Now it's just good old fashioned SOHCAHTOA as long as we stand right here. So I'll even go through like we did earlier and label everything. So if I'm standing right here, that means my opposite's over here, my adjacent's right here, my hypotenuse is right here. Let's do it. Now it's just a matter of getting these numbers in the right spots, the 5, the 13, and the negative 12. So sine, let's see, sine is opposite over hypotenuse. So I should end up with a sine of that angle is 5 over 13, 5/13. Cosine would be adjacent over hypotenuse. So this is the first time we're seeing a negative cosine, but other than just saying, hey, it's negative, I don't think it really means a whole lot to us right now. Say, okay, the cosine of this angle is negative 12/13. And then the tangent is opposite over adjacent. So 5 over negative 12. Nothing changes for these three, right? These are reciprocals of these functions. So we'd say, all right, this is 13/5, 13 over negative 12, or, some people just throw, I'll do it on this one. You could just put the negative out front and just say that this is negative 12/5. So it's not necessarily, doesn't make a difference if I keep it with the negative. It's a negative number, right? Negative 13/12, negative 12/5. So it's almost like, all right, well, a little bit of work. We're, I'd argue not a ton of work. We create a right triangle. We know where to stand. We label our opposite, adjacent, hypotenuse. That's all stuff we've done. But now the cool part is all these numbers aren't actually technically for this theta right here. Those are applying to this bigger obtuse angle theta. So that's where the negative comes into play a little bit. So there we go. All right, that's kind of the first part. That it's like a bridge in the gap from right triangle in space trig to let's get on the coordinate plane and apply this to a more standard, kind of setting. So, all right. I think, did we get anything done? Evaluate the 6 trig functions for a quadrantal. Oh, we haven't even gotten that part yet. Oh my gosh. So here we go. This is where it really gets kind of, we'll start to be able to check some stuff off here in a little bit. We need one more piece of information. So definitely get up a new heading here called the unit circle. So it's like, here's what we're doing. We're basically saying, yeah, that was pretty good. I like what we just did there. We defined all this stuff, y over r, x over r. But we still have kind of a problem in that, and I'll come back here to the unit circle in a second. But, and I'm going to try to make it bigger. I don't necessarily want to have, so let's say my circle sometimes is this big. Let's say my circle is sometimes this big. Let's say my circle is sometimes this big. Let's say, can we find there's a room to squeeze one more in between there? Okay, so I got all these different circles. And now I'm going to use, let's see, what's a color I haven't used yet? Green. Let's draw an angle in standard position. All right, one side gets stuck right here. One side, sure, we can put it in that same spot where we've kind of been. But what's the deal here? You end up with this theta from here to here never changes, right? It's one set fixed angle measure that's not changing. But if I start asking those same questions that we just did a second ago and say, what's the sine, cosine, tangent of this theta right here? Well, it's not that it's going to change, but depending on what circle I'm looking at, am I looking at the brown circle? Well, now I'm working with this really small right triangle where these numbers are still going to be fine. I'd have to know that xy value, x1, y1, which is fine. Whatever, I can do it. Different radius, smaller radius. You say, wait, hold on. I'd rather work with this triangle. It's bigger. I got a little bit more room to work. Well, that's a different x2, and that's a different x and y coordinates, different radius. The radius is bigger. And you say, well, you know what? I'd rather work with this right triangle right here. It's a little bit bigger. And then you kind of get the point, I think, that which triangle should we work with? And the answer is basically, well, take your pick. The numbers aren't going to change. The ratios are going to stay the same. But instead of having this option and even leaving this an option, what we're doing with the unit circle is saying, let's just work with the same circle every time. Right? Because here, what does it matter if I use the big one or the small one? The triangles are going to have those same ratios. Okay, so hopefully we follow a little bit there. So I'm almost going to unpack this here and say whether, if my theta is right here, right, that's what my theta looks like. let's just use a unified circle that's always the same size, right? So what we're basically going to do, kind of the big reveal, if you paused and wrote this already, you're seeing we're going to set that radius to always be 1. So this distance from here to here is 1. Okay. And what's the big advantage? What does that do for us? It basically says that, hey, when I get on this, what we're calling the unit circle, and I see, hey, if I'm able to figure out these coordinates of this point right here, we're still using those same definitions that we had a second ago, putting the y coordinate over 1, or I'm sorry, y coordinate over r. Right? We just had that y coordinate over r. But now we're saying r is never changing. R is stuck at 1. So y divided by 1 ends up being y. Here's the big takeaway. Here's the big, like, what do we need to know? This is must-know material when we're on the unit circle, which I think from here on out, the rest of this lesson, we're going to want to be on the unit circle. The cosine of an angle is equal to the x-coordinate. Okay, if I know the x-coordinate, that's my cosine. The sine of an angle is equal to the y-coordinate. I don't know how you're going to remember it. Sine, y, they got the same sound in the middle there. I don't know. And then tangent actually doesn't change from our previous definition. So if I look here, what did we define tangent as? The y-coordinate over the x-coordinate. So that's going to stay that same definition, that because we're not messing around with radius in that one. That has nothing to do with radius. So the tangent of an angle is equal to the y-coordinate over the x-coordinate. Okay. Put a big box star around it. We'll reference that, I think, probably throughout the rest of the lesson. A lot of it, not all of it, but that's kind of a big deal for us, okay? All right, let's take a look. What do we got? Well, actually, one more thing here. One more vocab word for us. And then we'll take a look at an example, okay? So quadrantal angles, I think it came up maybe at least in the previous notes, maybe not that word specifically, but we did look at some. It's an angle in standard position whose side that's moving, remember the terminal side is the one that kind of swings around, falls on either the x or the y axis. Okay, so it's another way to think about it would be an angle whose a multiple of 90 or negative, moving the other direction, negative 90 as well. So it's kind of our big landmark spots, which we'll see here in a second. When we get on the unit circle, we're talking about this point right here, this point right here, this point right here, this point right here. Why are those a big deal for us? Because those are the only 4 points on the unit circle where I actually know what's this distance again? 1, right? We're setting the radius at 1. So I actually know true coordinates of this point right here as 1, 0. Right, I went right 1, up or down 0. Here, what are the coordinates here? That's 0, 1. Over here, what do we got? That's negative 1, 0, and then down here is 0, negative 1. Okay, these other ones in here, that's going to be a little tougher to figure out what is the x and the y coordinate. But we have these 4 nice points that hopefully by now we've kind of connected to angle measures, right? 0, 90, 180, 270, 360, and so on. And we just got done talking about, hey, x coordinate is cosine, y coordinate is sine. Yeah, we can start to answer some of those questions without really thinking about it. Without, hey, I shouldn't say that without thinking about it, but a little easier using kind of this information, cosine of theta is equal x coordinate. I'll probably go back to the slide a few different times, but that's going to be big for us. So let's take a look here. I got an example. You'll see what kind of the question, what the question might look like. So we're looking at a section of maybe an assessment that I'm asking you, hey, calculators, put them away, put them underneath your desk. Not allowed to use a calculator on this problem. But I still want to know, look at that, look at the question. Evaluate the 6 trig functions. Oh my gosh, we're still asking this. So I'm asking you, what is the sine of not just theta anymore? I'm giving you an angle measure of 450 degrees. What is the cosine of 450 degrees? What is the tangent of 450 degrees? What is the cosecant of 450 degrees? What is the secant of 450 degrees? And what is the cotangent? Okay. No calculator. Oh my gosh, how can we do this? That's a huge angle measure, 450 degrees. Well, if I'm asking you to do this without a calculator, you got to believe that it's gonna end up that we're gonna have to probably end up on one of these spots, right? Because we said if I know, I'll just rewrite it here. I'm gonna shorten it up. That x, I guess I can't shorten it up. X coordinate equals cosine. Y coordinate is the sine of theta, and oh boy, x, let's just say, oh boy, getting worse here. Y over x. Oh, and I changed colors too. Y over x. That's my tangent. So that information coupled with what we're talking about with quadrantals, let's go. Where are we? This whole question kind of boils down to where on this unit circle am I? So where's 450? I would say if you need to, you could go old school and just 450 minus 360. I would say, why don't we count our way there? Here's 0 degrees, 90, 180, 270, 360, 450, right? You're kind of just basically your multiples of 9, 18, 27, 36, 45. We should be able to handle that. So 450 degrees is right here. That's where we're at. What are the coordinates of that point? That actual point on the unit circle is 0, 1. That's the only point I need to know right now. I don't even need to put those other ones on there because that's where we're talking about. 450 degrees puts us around and puts us right there. Okay. What's my x coordinate at that point? 0. Okay. That's my cosine. What's the y coordinate of where we're at? 1. Okay. That's my sine. Now we got to be a little bit careful here. When I take the y coordinate and put over the x coordinate, fine. Y over x is 1 over 0. Let's simplify that. What is 1 divided by 0 without a calculator? Is it 0? No. That is, we should say, don't just leave it 1 over 0. That's not, you're not finishing it. We should say, and I'm just kind of writing it sideways here so I can squeeze it in, but that's undefined. So the tangent of 450 degrees is undefined. If you don't believe me, type it in your calculator just for the sake of checking, Mr. Kroll, and say, oh yeah, that's right, I got an error. It's undefined. Okay. And the nice part here, we don't have to relearn anything like, oh my gosh, there's something new for cosecant, secant, cotangent. It's not. I'll just maybe off to the side here, like or below. I'll just do it right here. I need to flip these numbers over. Right? I need the reciprocal. So how do I flip this 1 over? Well, I kind of want to see it as a fraction. What is that? What does 1 look like as a fraction? Oh, it looks like that, 1 over 1. So I flip it over, I still get 1. What is 0? What does this 0 look like as a fraction? That one's a little tougher. Sometimes people struggle with that. What does 0 look like as a fraction? It's still, I think, going old school. Like, how do you turn a number into a fraction? Just put it over 1. So 0 over 1 is 0. When I flip that over, I get the same thing. I get 1 over 0, and that's no good, at least as far as simplifying. So we're going to say also undefined there. And then kind of interesting here, we go from originally being undefined for the tangent of 450, but if I flip, reciprocal, this 1 over 0 becomes 0 over 1, which now all of a sudden is okay to do. 0 divided by 1 is 0. So that's what we ended up with. 1, 0, undefined, 1, undefined, 0. Okay. So there we go. I'm going to just throw out there for a second, not a whole new problem, but just to kind of see, what if I asked that same question, same setup, same everything, give the 6 trig functions, but except I said theta is equal to, let's make one up here, negative 7 pi over 2. Okay. So I think this is probably for a lot of us going to be a step up in difficulty, right? Why? Just because it's in radians. So the process is still going to be the same as far as I need to know which of these locations am I, or like where am I at? And once I know that location, it's ones and zeros, zeros and ones, and negative ones. That's fine. I think the hard part on this one for a lot of us is like, where I can't use my calculator. That's underneath my desk. Are you sure? So I'm going to offer a few things here. I'll show you two things you can do. You either got to go old school with it, or not really that old school. I keep saying that, but this is actually probably more recent school, as in like the previous lesson. We got to do pencil and paper, convert that back to degrees. So, here's me. I got to take my word. I don't have my calculator in my hand. I'd reduce my pies. I would actually reduce the 180 over 2. What's 180 divided by 2 is 90. And then do 9 times just 7. Just, I can keep it as positive for right now, is 63. So this is going to be, and then we'll tack a 0 on the end. So negative 630. So yeah, that gets me to degrees. But I still think some of us are like, okay, that's great. Where is that? So I think that I would probably say, can we count by nines? 9, 18. I don't mean to sound dejected or anything like that, but sometimes I get a little frustrated that we're in an advanced algebra class, and I get a lot of pushback sometimes on counting by nines here. I've stopped counting, so what am I doing? 9, 18, 27, 36, 45. Well, there's my 63, right? So it goes back to let's just work our way around the circle. Let's use red here, and counting by nines. And what am I doing when I'm counting by nines? Counting by 90 degrees. So let's see here. 9, 18, 27, 36, and you're going to yell at me because I'm going the wrong way, but I'll fix it in a second. 45, 54, 63. Okay, that would be the positive version of it. So just don't miss, and I actually kind of did for a second there, that this is negative. So I'm going to put my pen on the paper and count the other way, but same multiples: 9, 18, 27, 36, 45, 54, 63. So the only thing that changed was my direction. So that's, again, putting us right at that same spot. Nothing's going to change. Actually, all 6 of my answers would be exactly the same for this one. So that's something you can do. That's some work, though. This, converting, make sure we convert correct, understanding that, hey, I got to count by multiples of 9 or 90. I think the further along we get, understanding that, I think there's a lot of us that and basically I think everybody should know that this is pi over 2 up here, just on the if we're counting by radians, right? We've got 2 pi is all the way around, pi is over here, and halfway between 0 and pi is pi over 2. So one thing you can do as well is just, as long as I know, hey, pi over 2, I need to go negative 7 pi's over 2 the other way. Like I got to go backwards 7 pi's over 2. So I start counting and I go 1, 2, 3, 4, 5, 6, 7. I moved negative, and that put me right at that same spot. And that way I don't have to mess around with converting. I don't have to mess around with multiplying out multiples of 90. As long as you can kind of pick out from this that, hey, pi over 2, that's kind of the magic. If I can see that there and say, hey, let's just count by pi's over 2. I just need 7 of them. So you're basically going to count every 90 degrees. So a couple options there, but radians would make a problem like that, I think, tougher. All right. Let's move on here. We're actually doing okay. I think the rest of it, we got one kind of big concept left, and this last part will go relatively quick, okay? So here we go. Reference angles should be your next heading in your notes. So yeah, set that up. So what's a reference angle? We pretty much have been working with them this whole time. Maybe we didn't know it, but this is good here. The acute angle formed with an angle on the terminal side of theta and the x-axis. That's getting a little bit wordy, I think, for some of us. And then it starts getting into all this, and this, and this. Let me show you what a reference angle is. Let's go back to something we literally already have in our notes. The very first thing I think we talked about was right here. And we said, you know what? Let's put our little person standing at this theta right here. That's our reference angle. That acute angle that we're turning our triangles into, saying, well, my theta was boom, boom, boom. This humongous theta was gigantic. Negative, I don't even know, 900 degrees, not quite that far. But um, the theta that we're actually going to work with, that we put ourselves on the x-axis, that's our reference angle. Okay. So I kind of summarized it, I think, in my own words here to make it a little bit more, I don't know, just meaningful for some of us. Let's just clear this off there. So it's basically the acute angle formed by the terminal side and the x-axis. So you can kind of see in the pictures, it's up to you if you want to make the pictures, but if my original theta was just kind of a, whatever, there's my theta, what's the quickest way from this terminal side to get to the x-axis? Should I travel backwards the way I came? No, that's kind of the long road. We should be taking this short path. There's my reference angle. Okay, so it kind of just depends on where you're at. Here's a case of my theta is a little bit larger, and I say basically, all right, there's two angles back to the x-axis. Should I travel this way? No, that's the long way. My reference angle is always the shortest path back to the x-axis. I can't stress that enough. Sometimes people want to do weird stuff, and it's not to the y-axis. Don't do that. It's always back to the x-axis. And then you can see one here where we stop a little bit short. I travel past that 270 mark and say, all right, well, I think it all boils down to the same thing. How do I get back to the x-axis quickest? Well, this little angle right there, there's my reference angle. Okay. And basically what this last part is just saying, this is what's going to allow us to work with any theta. And we saw that already. So those big thetas, we trace it back to an acute angle. So I've got a couple here where it's just straight up, what is the reference angle? I think it is helpful to see a picture. I like to see it, but no, this would definitely be in a section that you have your calculator available to you. So I'm not asking you to do this. The only time I ever say that, how do I know? You're literally going to see no calculator, no calculator, no calculator, big, bold, no calculator. So unless it says that, where this one doesn't, find the reference angle, you can use your calculator. So let's do part A. What's the reference angle for 165? I definitely think the picture helps just to kind of know where am I at and what's the shortest way back to the x-axis. So hopefully this skill at least. All right, well, negative 165 would be over here somewhere. I don't quite get to 180. And that's almost like, oh, I didn't quite get to 180. How much further would I have to go to get to 180? And the answer to that question is our reference angle. So we stopped, we went backwards negative 165 degrees. The other thing I didn't say when you should probably go back to your notes and add here for reference angles. Let's just refer to that angle as always a positive angle measure. It doesn't do us any good to talk about it as negative. It's just one less thing to kind of mention. So just how much further do I have to go? I have to go 15 degrees to get to this x-axis, right? That's going to put me at negative 180. But let's just say my reference angle is 15 degrees. Do we follow there? It's how many more degrees do you have to travel to get to the x-axis? And that's it. The other thing that I should say, that these directions should include the statement answer in the same units as the given angle. So this one was in degrees, so I'm totally fine with leaving your answer in degrees. The second one, obviously being in radians, we should answer in radians. So I'm gonna try to keep working with. If you're a converter, if you need to convert that, go ahead, convert it, put it in degrees, do it. But then you got to put your answer back in radians. So it's a kind of a double convert problem. I'm going to try to keep pushing, working, just staying in radians. So I'm going to do that same thing that we just talked about. Pi over 4 is kind of what I'm seeing there. So, hey, pi over 4, what was that again? Pi over 4 is 45 degrees. So I just need to count every 45 degrees. So here's 45 degrees, here's 90, here's another 45, here's another 45, here's another 45, 45, whoops. Yeah, 45, 45. So those are I've basically divvied it up into 45-degree angles. And you're like, what is he talking about here? But hear me out here. If I'm moving 7 of these, I need to hit 7 of them. 1, 2, 3, 4, 5, 6, 7. There we go. That's exactly what 7 pi over 4 looks like. 315 degrees for those of you converting at home is what you should have got for that one. But yeah, that's where I need to get. And if I ask myself, Well, how much further do I need to go? I need to move one more pi over 4 to get there. So that's your reference angle actually ends up being pi over 4. It wasn't a coincidence. I'm not saying it's always going to work that way where it's, hey, whatever that is, because we could see this broken into eighths or sixteenths or something like that. But because pi over 4 was the shortest or whatever, that's this increment right here is a pi over 4, 45 degrees. So again, if you're converting, you had 315. How much further do you have to go to get to 360? 45 degrees. Oh, what's 45 degrees in radians? Pi over 4. Okay, so we need to be able to do that. Hopefully that's not too bad. It's kind of just like a skill that we're going to need for the next section, okay? Okay, we're getting there. Look at that. A couple more here. Stay with me. Last really big kind of concept, okay? I think the quadrantal angle stuff, no calculator is big. That the reference stuff is kind of skill that's going to help us right here, okay? So evaluating trigonometric functions. Really now, it's still not for technically any angle. And there's some steps laid out here. We'll do our own example, I think, with kind of steps. And so I don't get hung up here. I think we can jump almost to a problem here and do kind of a notes / example all in one, okay? I kind of want to hide that one because we'll do that one separately. All right. So what am I asking it to do? The directions it's covered up. It says use reference angles to evaluate a trigonometric function. Look at this one. Oh, we're back to give exact answers. No calculator, no decimals. Obviously, decimals are going to be tough because I don't have a calculator at my disposal. So let's jump in here. Let's get it going. So the first thing I want to do, what are we at? What's the question asking? What is the cosine of negative 225 degrees? You got to be crazy, Mr. Cole. How can I do this without a calculator? I say, all right, I'll show you. Finally, I'm glad you asked that question. So the first thing I want to do is find your reference angle. Okay, which we literally just got done doing. I think a picture is helpful. Let's see, where are we going to be at here? I'm going to go negative 90. It's negative, right? So negative 90, negative 180, and then, oh, okay, another 45 degrees. Can we do that without a calculator? If not, you got to subtract. What's 225 minus 180, or what's the difference between those? Oh, it's 45 degrees. So I'm seeing there's my theta. We went backwards, negative 20 or negative 225 degrees. Our reference angle is 45 degrees. Okay. Step 2. All right, cool. It's not bad. We can do that. We just practice it. This is the part. It's kind of a loaded step 2, but use our model, or let's use our special right triangles to I'll just abbreviate, to evaluate function. And even that's like, what does that mean? So hopefully hopefully you remember that we have two what we called special right triangles or model right triangles, our 45 45 90 and our 30 60 90. And look at that. What? 45 degrees. So basically what I'm kind of saying, if I ask you to do this exact with no calculator and no decimals, it probably has to, well, not probably, it has to trace back to either a 30 degree, a 60 degree, or a 45 degree as an angle's reference angle. That's the only ones that we can do exact. If I said, what's the cosine of negative 226 degrees, you'd say, I'm skipping this, Mr. Cole. I can't do that exactly. Okay. So, but again, like I said, it's kind of a loaded example too here. What do I need to do? I need to basically, if I don't remember, well, I need to remember it. I need to recreate, right? I haven't touched a calculator yet. My 45, 45, 90, and that's, I mean, the 45s, I think everybody remembers that. It's what are my side lengths? 1, 1, square root of 2. Okay, so what? Well, how would you do the cosine? So we're basically back to, so if you want to use the special right triangles, what do you mean use? The additional note would be use so ka toa to help ourselves out. Okay, so stand at either one, it doesn't matter, of the 45-degree angles. Label my opposite, label my adjacent, label my hypotenuse. Okay, no problem. Cosine is the one we're particularly interested in. So I'm going to go the cosine of 45 degrees is equal to the adjacent length right here over the hypotenuse length, which is the square root of 2. And we've done so much of this simplifying, it almost goes without, let's see, can I squeeze it in here? Square root of 2 over 2. So that's the cosine of 45 degrees. Now, that wasn't the original question. The cosine, it was asking for the cosine of negative 225 degrees. So we got one last thing to consider. So step 1, step 2, now I'm kind of going in a weird little path here. But step 3, I'm trying to keep everything. Oh, I like that pink. It showed up so nice. Can we fit it in here? How can we word this? Use x, y, or let's say use this. Use quadrant. You're like, what? Quadrant? I haven't seen that word in a long time. Use quadrant to determine that says determine sine as in not like cosine or sine, but like sine as in positive or negative. So I've got the number. I know for a fact the cosine of negative 225 is either the square root of 2 over 2 or the negative square root of 2 over 2. And you're like, well, that's pretty good. And I would agree. That actually is pretty good. You'd get a pretty good amount of credit if you can get to this number right here. So what I'm saying, use the quadrant to determine the sine. How do we do that? And this, I just have to scroll here a little bit. This still boils down to, it's the third time I'm writing this, the x coordinate we're associating with the cosine of an angle. The y coordinate we're associating with the sine of an angle. And the y over x we're associating with the tangent of an angle. Okay, so see if you follow here on this one. I've still got my picture, which I think we can use. We're talking about a point right there, right? So I've gone, what would be the coordinates of that point? You say, you're crazy, Mr. Kroll. I don't know what that is. But we went left some distance. So that means my x has a negative value. Hopefully we all agree. Yep, if you move left, you go, x would be negative. But then we went up to get there. So a y would be positive. Okay. So I'm ready to write and circle my final answer. I think I remember it was asking us for what was the cosine of negative 225 degrees. Well, we just said, hey, I could almost circle it here. I'll clear this. That's what I just erased. I'm just going to write it in black though. The square root, I thought I was writing it in black. Jeez, whenever I pick up that eraser. The square root of 2 over 2. And then I just got to look. Okay, cosine, I got to remember this. Cosine goes with x coordinate. What is the x coordinate of our location? Is it a positive or negative? Oh, I already made a note for myself. The x coordinate is negative. So my answer here, my cosine should be negative. So that's what we mean by using the quadrant. I'm trying to be short there and keep the notes to a little bit reasonable. So we went left. If this same question was asking about sine, obviously it would be a different number here. It's going to be opposite. Actually, it would be the same, opposite over hypotenuse. And that's neither here nor there. But the sine would be positive because we associate the y coordinate with sine. And in this quadrant, the y coordinates are positive. So it would be a positive value. I circle my answer. I pat myself on the back and say, wow, good job, Mr. Kroll. You did it. All right. Let's do one more there. And you're like, oh, no. But I think we're going to look at one in radians, which still, as I know, is going to be something that it's that one added element. We don't have the calculator in front of us. So I'm going to clear this here. Obviously, you can just scroll back 2 seconds and get anything that you missed. Let's clear it. Let's look at that one that I covered up. Oh, all that work gone. Right here. Great one to look at. Okay, what is the cotangent? So I'm just going to rewrite it. I don't need to, hopefully I can do it all with all the space here. What is the cotangent of 10 pi over 3? And actually, you know what? Maybe I'll just set this up as my answer blank right here. And I'll circle this as, hey, that's where we're going to write our final answer when it's all said and done. Okay, so first thing to do is figure out where the heck are we. I want this visual for two reasons. A, it's going to help us with the reference angle, but B, later on when I'm trying to figure out which quadrant I'm in, it'll be nice to have. So I still see this as, and I hope more of us are seeing it, when I see that pi over 3 like that, I'm saying, hey, I know what pi over 3 is. Pi over 3 is 60 degrees. So if I count every 60 degrees, let's see, there's a 60, 120, 180, 240. Not that I even really have to know all these numbers, but 300 and 360. Okay, hope it's that same deal. Can you count by sixes? 6, 12, 18, 24, 30, 36, and just tack a 0 on each one. Then you can count by 60s. So I got 60, 120, 180, 240, 300, 360. And how many do we need to move? We just need to move 10 of them. So once I got them all laid out like that, let's just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't forget where we were. We went around one full time and stopped right there. So it's that same idea, and I know I said it doesn't happen all the time, but for the most part, if I see that pi over 3, what's the shortest way back to the x-axis? One of those tick marks, one of those black tick marks that we highlighted, that's 60 degrees. So my reference angle is pi over 3, which is equal, we just wrote it up above there, is 60 degrees. So I'm trying to give us some options to work with, always having to convert to radians, or from radians to degrees and back and forth. So 60 degrees is kind of the magic number. If I want at this point, why don't I just do it here and say, all right, what are the coordinates at that point? We went left x, right? To get there, I'd go left x, and I'd go down y, which would also mean a negative y value. So I just see it. That way I know later on when I come back to it, it's there for me. And hopefully that part's not too bad to finish. All right, awesome. So I found the reference angle in radians, kept it in radians. Next step, I got to get in the correct triangle. So let's look at, I'll come over here. I need to see, and again, the angles are good. I mean, we need the angles in there, but what side length's opposite what? So the 30 and the 1 are always opposite. The right angle and the 2 are always opposite. And the 60 and the square root of 3 are always opposite. So it does matter where those go, because now when I go to put myself in this triangle, I'm of course going to stand at the 60 because that's our reference angle. I'm going to label everything accordingly: opposite, adjacent, hypotenuse. And what are we looking for? What the heck? Cotangent. We can't do this with SOHCAHTOA, can we? And I say, oh, I'm just being silly. Of course we can. I just need to know who's cotangent's partner. And that's the one that's pretty easy to tell, right? Cotangent goes with tangent. But instead of going opposite over adjacent, right, the reciprocals, I need to go adjacent over opposite. So, okay, that's not bad. I can still use SOHCAHTOA. It's just we got to flip-flop them here, adjacent over opposite. So where are we standing? I got everything labeled. I got my adjacent. So the cotangent of 60 is equal to my adjacent, which is 1, over my opposite, which is the square root of 3. No problem. Let's fix that. Times the square root of 3 over square root of 3. We're going to end up with the square root of 3 over 3. I am ready to write this in my circled little area here. The square root of 3 over 3. And just before I move on to the next problem, don't forget step 3 now. Was, okay, we got to figure out, is this positive or negative? I left a little room there to decide positive or negative. Tangent can be kind of tricky. I erased it once. Oh my gosh, do I got to write it one more time? Cosine of theta is equal to, we're associating with the x coordinate. The sine of theta, we're associating with the y coordinate. And tangent, we're associating with y over x. So it still kind of works this way. If the question asked me about secant, I would just look at the x. If it asked me about cosecant, I would look at the y. And with cotangent, I want to look at tangent. You could think of it as x over y, but we really only need the signs. So we said, hey, I got a negative x and a negative y. Well, what happens when you put a negative number over a negative number, whether it's x over y or y over x? If they're both negative, that would result in a positive, right? A negative divided by a negative is positive. So that would result in a positive cotangent in this case. So I'm done. I'm going to recircle this and just say, okay, I did think about the positive negative. It ended up being positive because it was negative x, actually technically negative x over negative y, which would result in a positive number. Wow, those are legit. But like I said at the beginning, they're always going to trace back to, like, there's a built-in hint there. I can't ask you to do this unless the reference angle is 60. The only one we didn't look at was a 30, which would be pi over 6, or 45 degrees. Okay. Yeah. So that's kind of the approach there on a problem like that. Get your practice. Those ones there's just a lot. They rely on a lot of information. That was new from this lesson. X goes with cosine, Y goes with sine, tangents Y over X. This location stuff, I guess, ties right to this, but sketching it, turning it back into a reference angle, that's new. This is old, right? The 30, 60, 90, SOHCAHTOA, using that information, rationalizing. Who's the partner, cotangent, tangent, cosecant, secant, cosine and secant. So that stuff's old, but it kind of all gets built into one big ticket question. So I love these questions because I can kind of assess where are we at with almost everything at once. So, all right, last slide. Look at that. We made it a little bit long here, but we've got this model. So we kind of finished the last lesson the same way, where I'm just trying to give you an example of where potentially might this come up. So it's another physics example. A lot of this stuff with the thetas and launch angles and arc measures and stuff like that, it has geometry and physics applications, but we were calling it the horizontal distance model. I'm not asking you to memorize this. I would always provide something like this for you because it's kind of just an obscure, like, oh, hey, this one instance you need to use this. So I really need you to know like what this stuff stands for. So it's a distance model. Everything's in feet. So your answers will be in feet, and then in velocity or your speed will be in feet per second. And so we need to know basically if I want to find a horizontal distance that something is launched at, or I'm sorry, that something travels, I need to know the initial velocity or the initial speed at which it's launched, and then at what angle was it launched at. So let's give it a shot. I know this example here is pretty much just like a good old-fashioned plug into the formula type of thing, but even that with sine and 2 theta, I know for sure it gives people trouble sometimes. So we kick the soccer ball. We can make a little picture. I don't think you have to make a picture, but whatever. We're already at close to an hour on their notes here. We might as well we kick the soccer ball. Whatever. It travels from here to here. It's telling us our launch angle is 30 degrees. Whoops, theta equals 30 degrees. So we kicked it at a 30 degree. Apparently my foot is able to kick it at 46 feet per second. How far will it travel before it hits the ground? So, yeah, I mean, like I said, I don't think you have to make that picture. We're looking for distance equals, what's my initial speed? 46 feet per second. So 46 is going to get squared at some point. I'm going to divide that by 32, which I believe is a gravitational constant. We're going to multiply. There's a times in there. The sine of, here's what I would do. It's instead of having like one more calculation on my calculator, this is talking about twice the launch angle. So don't do the sine of 30 right here. I need to use the sine of 60. I need to just double that. And it's just such an easy one to do without the calculator. So why don't we just, do it here? And that way it's just one less thing I have to put in the single operation. But other than that, I think I can hit this whole thing as long as I'm being careful on how things go in my calculator. Let's see, let's do it. 46 squared. I don't know the answer to this. 46 squared divided by 32 times the sine of 60. How do we do? So the ball traveled. Is that a good kick? I honestly have no clue. 57.3 feet. So the only potential wrinkle you could see here with this formula, and I don't mean to extend the video any longer than I have to, but similar, type of question. What if I said, hey, you traveled, you kicked the ball and went 75 feet. At what speed did you kick at? I'd probably get yelled at if I was in English class or even probably a physics class. What speed did you kick at? But could we use this formula to solve for V? I think so. So basically what we would have is, all right, the ball traveled 75 feet. I don't know what speed I kicked it at. Here's my gravitational constant. Let's go back and say I kicked it at I need another piece of information here. Sorry. We kicked at or launched at, let's use that same 30-degree angle again. So I'm going to use that sine. Remember, I've doubled the angle 60. Okay, so if you can't tell, I'm making up an example here. But just to kind of show you that we could still use this formula to find something else. The launch angle, I don't think I would ever ask you to find. But anyways, how would I solve this? That's kind of the thing. The whole reason I'm doing this is because I don't know if everybody knows how to solve this right here. The first thing I would look at doing is probably multiplying both sides by 32 just to get this 32 out of here. Okay, so I'm going for my calculator and kind of going and showing some steps here. 32 times 75, just because I know it's at least going to be a decent number. 2400 equals V squared times the sine of 60. So now I'm probably going to stay on the calculator the whole time. So hopefully you can follow me here. Here's what I'm going to type in. I got to get rid of the 60. I'm sorry, don't just do 60 like I'm writing. So I'm going 2400 divided by I'm just pushing the division button, divided by actually the sine of 60 degrees, push equals, it's going to stay a decimal, 2771 on my calculator is what I'm getting right now. I'll jot it down, but stay exact if we can, 27128, da, 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 da. I'm keeping it on my calculator. I'm not clearing it, is equal to my initial speed here. And then how would we finish that? I need to square root both sides. So on my calculator, I can push square root of second answer, and that allows me to stick this right underneath the square root without clearing or anything like that. And so we kicked this ball apparently at an initial velocity, initial speed of about 52.6 feet per second. So just a different look. Like I said, I know some of us I'm burnt out myself, so it's kind of a long lesson. But yeah, there we go. So let's go check it out. Obviously, I'm out of slides, so I got to be. Oh, look at that! I even added 1, 2, 3, just kind of made up in the middle there. I think we better have done them all, right? Have we done evaluate the quadrantal? Yep, no problem. That was the 45, or I'm sorry, the 90 multiples of 90. Reference angle for any given angle, no problem, both radians and degrees. Evaluate trig functions for angles that are multiples of 30 or 45 without a calculator, right? That was the big one we just finished with. And then the formula for horizontal distance projectile. Whew, big old sigh of relief there. We got it done. So hopefully that helps. I'm done with 9.3. I will see you in future lessons.